All right, chapter 9, right triangles and trigonometry. Trigonometry is the science that's actually based around right triangles, and trigonometry goes a lot more into detail, whereas the actual name of right triangle is far more general. It just really talks about the shape itself, the fact that I'm dealing with a triangle that has a measurement of 90 degrees somewhere in it. But trigonometry is going to deal with the science of how I use right triangles, and it tends to be one of the most commonly used geometric forms in the world. Okay, used in construction, used in engineering, used in location development. Okay, the whole 9 yards. It's used all the time. And in this section, we're going to explore the most commonly associated item with a right triangle, and that's the Pythagorean theorem. Arguably the most popular, the most famous math formula of them all: a squared plus b squared equals c squared. So fundamentally talking again about what like the namesake of this unit is, right triangles. Okay, so first off, a couple of things, just even more general. Triangles in general, three-sided figures. One thing that's going to pop up a lot throughout this chapter is going to have to deal with the angle measurements inside of triangles. So a couple of things to just have as background knowledge, good stuff to throw in the margins of these notes right now. Okay, triangles, the sum, if I were to add up all three of the inside angles of a triangle, most of us know this already, but all three angles need to add up to 180 degrees. Okay, so the subset of that being right triangle specifically, one of those three angles is forced to be 90 degrees. So this is a unique subset of triangles in general. So if all three angles have to add up to 180 degrees and one of them is 90, that leaves 90 degrees left over to split between whatever the other two angles are going to be. We'll go a little bit more into detail on that as we move forward throughout this lesson. But this set of right triangles is, again, used all the time in real world stuff. And the Greek mathematician Pythagoras was the first one to postulate this theorem, and that's why it's given his name, the Pythagorean Theorem, that a squared plus b squared, that the legs, the side lengths of each leg of a right triangle, the legs are the ones that make up this right angle. If I were to take each of those side lengths, whatever those measurements are, and square them and add them together, they always will equal the square of the third side, the longest side of the triangle. This hypotenuse, as you will likely know it, has to be the longest side of the triangle. Okay, and so the sum of both of these squares has to equal the square of the third side. That was Pythagoras's major claim to the mathematical world, and it has paid off ever since. Okay, it is the most famous of all of the math theorems. Okay, so a couple things to be aware of again. All three angles inside every triangle have to add up to 180 degrees. In a right triangle, one of them has to equal 90 degrees, leaving 90 degrees to split between the other two angles. Another fundamental thing to know is that the hypotenuse, or the side that's opposite the 90-degree angle, always has to be the longest of the three sides. And there's a fundamental reason why that hopefully you remember from previous geometry units. There is a relationship between the size of an angle, the number of degrees it is, and the side that is opposite. What I mean is this, that the larger the angle, okay, the larger the angle, for instance, if I do a really wide angle like this, all right, okay, the size of that angle increases the length of the side that's opposite that angle. Okay, so we have a longer side here, as opposed to a very small angle like that one, where now because this angle is smaller than that one, it again affects the length opposite, and I get a much shorter side opposite a small angle than a longer side opposite a large angle. So because of this fundamental relationship between angles and side length, if I have three angles in the triangle, the largest of the three angles, which in a right triangle has to be this 90-degree angle. The 90-degree angle has to be the largest here because there's 90 degrees left over to split between those two. Neither of them can be 90 degrees again. So the largest of the three angles is the 90-degree angle, and because of that, the side opposite that 90-degree angle will have to be the largest of the three sides. And it kind of walks down after that. So then like the next smallest angle will have the next largest size. The smallest of the three angles will have the smallest side. Again, we'll explore this relationship a little bit more deeply in section 2. But these are good fundamental things to have knowledge of going into this section. Okay, but back to just a squared plus b squared equals c squared. This is something that we all will kind of at some level have been familiarized with. You've probably done problems like this already throughout middle school and Math 1, but this will be the focus of this section. And we'll look into different ways to do it, just mostly to review how to do it. But if you're like me when I was in high school, maybe you're wondering where the formula even came from. So in here in the margin, I've given you a little bit of a proof about where it comes from. I can go into more detail in this. I'll attach a video on our Google Classroom that goes into detail in case you have that curiosity. Because when I was in high school, I was always of the mind, like, where did these formulas come from? Someone just didn't have like a nightmare and pulled out this formula out of nowhere. These do come from somewhere. And the original mathematician Pythagoras has his own set of proofs, but the one I include here is actually one that's referenced by one of our former presidents, James Garfield, who also happened to be a mathematician and did this kind of stuff as a hobby on the side, came up with a proof for Pythagorean theorem. And so, again, I'll attach a video that goes a little more into detail into this, but I show the start of it here. It involves the use of a trapezoid and the area of the trapezoid in order to solve it. I'm not going to go into detail into the video here because we got more stuff to get into, and I'm not going to test you on that kind of stuff. But if you are curious as to the origination of where the formula came from and why it works, we can go into that in another video. All right. Next thing I wanted to just briefly bring up here, you see this long list of numbers. It can seem a little overwhelming. These are known as what we call Pythagorean triples. And just breaking down this list, these orange triples that we see here in the top row, these are what we would call fundamental Pythagorean triples. And then in the columns, there are multiples of each of those. So let me just kind of break this down. What is a Pythagorean triple? Simply put, it's this. And I leave a little note right here. There are three non-decimal results, and that's very vague. I tried to put it in terms that maybe you'd be able to latch onto. Essentially, they're this. A Pythagorean triple is three whole numbers that follow this formula. Okay, because I can't just randomly chuck numbers at this necessarily and make it always work with nice, friendly numbers. Pythagorean triples are unique combinations where a squared plus b squared equals c squared. All three values, all three side lengths are nice whole number results. That's actually kind of a unique thing. And as such, you're going to be asked a couple of questions about like, hey, like solve for this missing piece of a right triangle. Did the result demonstrate a Pythagorean triple or not? Essentially, it's just a fancy way of saying, did you get three whole number answers, three friendly side lengths for each side of the triangle? So again, just to kind of point out the point I was making before, for instance, this guy over here, 7, 24, and 25. If I were to say like, hey, these are three sides of a triangle, of these three sides, you should be able to identify which one is the hypotenuse. The hypotenuse will always have to be the longest of the three sides. So in this case, the 25 of these three numbers would have to be the hypotenuse. It would have to be C. In other words, I could have a squared plus b squared equals c squared. So let's test that. So if I were to do 7 squared, that's 7 times 7 or 49. 24 squared, if I were to do 24 squared on my calculator, is 576. If I were to add that 24 squared, or 576 plus 7 squared, or 49, I get 625. If I were to take the square root of that, thus solving for C here, so if I were to take the square root of that, notice I get a nice friendly result, 25. These are what we call a Pythagorean triple. And the only significance is that they happen to be three friendly whole numbers. Okay, this is one we would call a fundamental Pythagorean triple, meaning that this is like each of these are the lowest factor of each. So for instance, like the row beneath it, this 14, 48, and 50, I simply took the 7, 24, 25 and multiplied them by 2. And in this case, 14 squared plus 48 squared will equal 50 squared. So that's still true. It's just that this is just a multiple of the fundamental. So anyway, again, I went into a lot of detail there. Essentially, the only way that you're going to be using this in your assignment will be that you'll be asked to, you'll see this in a second, you'll be asked to solve for a missing piece of a Pythagorean of a right triangle, and it's going to ask you, does this represent a Pythagorean triple or not? So let's see this in example form. These should be very familiar to you from previous times you would have gone over Pythagorean theorem. So you're going to be given a right triangle as shown in the diagram, and you're going to be asked to solve for a missing piece. The difference here with this question, just kind of referencing what we talked about up here, is that you're going to be asked to find a missing variable, the variable x in this case. And then based on that result, you're going to determine whether or not the three sides form a Pythagorean triple. That part's real quick. Basically, you'll notice that both side lengths that they gave me in both examples are already whole numbers. Essentially, if I solve for x and it happens to be a nice friendly whole number again, it's a Pythagorean triple. If it ends up being like a decimal or some weird fraction and stuff, it's simply just not a Pythagorean triple. It doesn't mean anything like it's still a right triangle. That stuff still applies. It just means it's not the special case of a Pythagorean triple. All right, so I'm going to go ahead and just do one of these. I'll do part B here just so we can get re-familiarized with how to solve using Pythagorean theorem. All right, so again, this is part B. Very common type of question with right triangles and using Pythagorean theorem. You'll be given a right triangle. Okay, and it'll be obvious it's a right triangle because it'll have this little perpendicular box in the corner. And then you'll be told some information about some of the side lengths. So in this case, we were told that this one's 7 units long, this one's 14 units long, and then the piece that we're asked to solve for is down here. It's one of the two legs. All right, so here's my technique for how to figure this out. The very first thing I always take the time to identify is the hypotenuse. So just to remind you, the hypotenuse will always be across from the 90-degree angle. It will have to be the longest of the three sides as well. So when I ultimately solve for x, it'll be worth checking, like, just to make sure that it is in fact shorter than the longest side of the hypotenuse here. So this one has to be c. In the a squared plus b squared equals c squared, c has to be my hypotenuse, the side opposite my 90-degree angle. Whether or not I'm given a number or a variable, just c has to be that. All right, and then it actually does not matter which one's a or b after that. It doesn't matter which order I put it in, because ultimately 7 squared plus x squared will be the same exact thing as x squared plus 7 squared. Okay, so I'll go ahead and designate this one A, and I'll designate this one B. But it didn't matter which one was which. This is the one that matters. So as long as I can identify a hypotenuse, you're ready to go. So a squared plus b squared equals c squared. This will be ultimately what I'm plugging into this formula, the Pythagorean theorem. So I designated A as the 7-unit side. So this will be 7 squared. B was my unknown x. So that's going to be x squared here. And then C, my hypotenuse, was 14 units here. Okay. And you'll see the other examples. Example A, for the record, had x as the hypotenuse. So as long as you can identify hypotenuse, you'll be able to set up your equation. Pieces of this I can actually solve for on a calculator. 7 squared is 7 times 7, or 49. X squared is still x squared. 14 squared, or 14 times 14. If you don't know how to do this, most of you guys will have this on your scientific calculators. Let me just zoom in so you can kind of see it. Most of you will have this little shortcut button, x squared. It's a quick little button you can just push for what you're trying to solve for and stuff. But in any case, you could always just do 14 times 14. It comes out to 196. You can double check that. All right, and again, my task here is to solve for x. So I want to get this guy by itself. Essentially, now it's just a traditional algebra problem. I'm going to move stuff away from the x. So this positive 49, I'm going to subtract it from both sides, so that I get x squared is equal to 196 minus 49, which comes out to 147. And then hopefully you remember this from early in the year, but in order to get rid of this exponent, this squared, I'm going to do the inverse of sending something to an exponent, which is called taking a root. So the opposite of squaring something is taking a square root. So that would give me x is equal to the square root of 147. Now, if you were to plug this into a calculator, you would find that you get a long decimal. It comes out to 12 point something in a calculator. But be aware that they may ask you for an exact solution. Technically, this is exact, but it's not completely simplified. Okay, this is the exact solution. Doing this in a calculator, taking the square root of 147 and rounding it to like the nearest tenth and stuff would be what we call the approximated solution. But if they ask for the exact solution and fully simplified, I'll just remind you of what we did in a previous unit this year where we had to simplify radicals. I would check to see first, can I take the perfect square of this? I cannot. So then I would check to see if any perfect square can divide perfectly into this. My perfect squares are 4, 9, 16, 25, 36, 49, so on and so forth. I'll go ahead and skip to the punchline here. That 49 divides evenly into 147, 49 times 3 specifically. So 49 times 3 is still 147, so these two are exactly the same. But the reason we do this is because now I can use this property that I can split it up like so. And the reason I would do that is because this I can actually simplify further. I can take the square root of a perfect square. In this case, 49, square root of 49 is 7. And that would be left, the square root of 3 can't be simplified further. So this would be the fully simplified result. Technically, this is the exact answer. This is just the simplified version of that exact answer. If it asks you to round to the nearest tenth, this can be done on a calculator, either by going back here to just square root of 147 or doing this one where I take the square root of 3 and then multiply that result by the 7 out in front. That gives me about 12.1. So if it did ask you to round to the nearest tenth, this one will come out to about 12.1 units. But again, a lot of the time it's going to ask you for an exact solution. Okay, so we found the missing piece using Pythagorean theorem, came out to about 12.1 units if we use the approximated result, just double checking see if that makes sense. Again, of the 3 sides, the hypotenuse here should be the longest of the 3. If I got about 12.1 for my approximated solution here, you can see that's less than the 14. That checks out. We're good to go. All right, so that's that problem. Hopefully that was a bit of review. Depending on what they're asking for your results and big ideas, it'll depend on whether or not you need to simplify the radical or just use a rounded answer and stuff like that. All right, moving on. This is going to represent kind of the flip side of the same coin. So we're still using Pythagorean theorem for the record, but this is just the other way it's going to be phrased. Tell whether each triangle is right. What does that mean? Basically, notice that in both of these diagrams, they tell me nothing about the angles. Namely, what's missing is that little perpendicular box hanging out in one of the corners, right? I don't see that in either of these triangles. So in this case, it's just representing the fact that in some cases, I know all the side lengths. I just don't know whether or not it's a right triangle. But essentially, this is just asking the same question. Use Pythagorean theorem to determine if it's a right triangle. Essentially, it breaks down like this. We're almost always used to the last type of problem. Hey, here's a right triangle. I can use a squared plus b squared equals c squared. But the converse of that is actually also true. That if I have a triangle, like in both of these cases where I know all 3 side lengths, if a squared plus b squared equals c squared, then that triangle must be a right triangle. So it actually helps me determine an actual angle measurement if that turns out to be the case. Okay, so let's explore that. I'm going to do this one because this one tends to be the scarier of the two, but let's go ahead and tackle this on the whiteboard. All right, and essentially, again, this is just the flip side of the same coin as far as the question goes for dealing with the Pythagorean theorem. So this is example B for example 2, and we're given the following triangle. All right, and we're told nothing about the internal angles, but we are told the side lengths. We're told that this one here is 36 units long. We're told this one here is 15 units long. And then we get this scary looking guy right here that tells us that this side is 4 times the square root of 95 units long. Okay, so I have 3 side lengths here. And if I'm going to test this with a squared plus b squared equals c squared, here's why I want to emphasize this again. The most important piece for Pythagorean theorem is which side is the hypotenuse. And in order to figure that out, if I only know the 3 side lengths, my hypotenuse should be the largest of the 3. But this guy's in a really funky kind of description right here. These ones are very easily to see like, all right, well, 36 is bigger than 15. All right, that's straightforward enough. No need to go into deep thought there. But this one is weird. And so here's my suggestion here. Pull out a calculator and give yourself a little approximation. So what I would do here is I would just simply figure this out in a calculator so that I can approximate it. so that I can at least have something to compare to these two. Because as it's written, I have no idea whether or not it's bigger. It looks like it might be longer than these two, but let's double check. So in this case, I would first take the square root of 95. Comes out to a long decimal, not surprising. And then I have to make sure I multiply by that 4 in front, and I get this ungodly decimal. But it approximates to about 39 units. All right, so what was the purpose of that? Why did I bother with doing that? Because now I have an approximation of this side length, and now we can clearly see that of the three sides, this is the longest one. And it's confirmed with this value. Just because this guy had like a 95 in it doesn't necessarily mean that it's the biggest side. It's once I actually approximate this, now I know clearly that of the three sides, this one would have to be the hypotenuse if it's a right triangle. So that tells me that this must be C if I'm going to test this for a squared plus b squared equals c squared. And then it doesn't matter which one's A or B beyond that. So we'll call this guy A, we'll call this one B. Okay, and now I'm going to test a squared plus b squared equals c squared. So fundamentally, when I start with these problems, just first, in some cases, they'll all three be whole numbers, and then it's just straightforward. Which one's the biggest? That side's C. If you get problems like this, just double check it, because in some cases, in this case, it worked out that it was the longest, but in other cases, it might be one of the other ones. So this just confirms which one's the longest of the three sides. And that helps me because it determines my hypotenuse C. But now I can apply a squared plus b squared equals c squared. And I know all three sides. So actually, technically, what I'm checking is, do these two things equal each other? If a squared plus b squared, these two guys here, if their sum does in fact equal the square of this guy, whatever this turns out to be, then it's a right triangle. If it doesn't, it's not a right triangle. So let's test that. So plugging in stuff here, I designated 36 as the A, so this is going to be 36 squared. Designated B as the 15, so that's going to be 15 squared. And then pay attention to this. I'm not going to use the approximated version. This was simply to let me know which was the longest side. But now I'm going to go back to the exact solution that I expressed it as, which is this 4 times the root of 95. And I'm going to square that. This one's scary, so I'm going to tackle this one last. Let me start with the ones that are a little more straightforward. Because at this point, now it's just doing some calculator work. All right, so 36. 36 squared gives me 1,296 plus 15 squared. 15 times 15 or 15 squared gives me 225. Okay, now adding those two values together gives me 1,521. So at the end of the day, when I go through a squared plus b squared, I get this result of 1,521. What we're going to find out is whether or not that ends up matching the c squared over here. But this one's a scary one. So let me deal with this guy now. All right, so here again is where we're going to use a property that we've talked about in the previous unit. Anytime I have a group of something that's raised to an exponent, I can distribute that exponent throughout that object. So here that could be expressed like 4 squared times the square root of 95 squared. Okay, so again, I distribute that exponent throughout here. Now these pieces I can do individually. 4 squared is an actual number. It's 16. 4 times 4. This is one that's weird for a lot of people, but what happens here is I have a square root that is then squared. What we're going to end up doing is undoing the radical. In other words, I'm left over with just the 95, no radical. Square root of 95 times the square root of 95 gets rid of the radical, and it's just 95. Well, now I just have a simple multiplication problem. So here I have 1521. Does it in fact equal this product? And so let me just double check that right now. 16 times 95 gives me 1,520. So let's look at that result. Let's see what happened. So when I did a squared plus b squared, just that left-hand side, it came out to 1521. We can quite obviously see this does not equal the right-hand side, which was just the c squared, the hypotenuse squared, which was 1520. So what does this mean? It means that a squared plus b squared does not equal c squared. That doesn't mean that this triangle doesn't exist. It just simply means that it is what we call not a right triangle. It's not a right triangle. There is no 90-degree measurement on the inside of this triangle. Okay, so we use Pythagorean theorem to confirm or deny whether or not this was a right triangle. That's the other application here. Had these two numbers equaled each other, then it simply would be a right triangle because a squared plus b squared did equal c squared. But that's just the alternative. Okay, so that's how you can use it here. Again, the major hint here is that if you get weird stuff like this, just approximate it first. That way you can determine which side's the longest for that c value, that hypotenuse value. All right, one more thing to cover here before we wrap up section 1. And it deals with a similar related concept that we just covered. Okay, this is called the Pythagorean Inequalities Theorem. Now, this deals directly with what result we just got. What happens when a squared plus b squared doesn't equal c squared? All right, it simply means, like in the most simplest form, it just means that there's not a right triangle. Okay, well, what other kinds of triangles are there? And here's where we'll see two more key terms that you've likely come across before. Acute means less than 90 degrees, and obtuse, which means more than 90 degrees. Those are the other two options. Essentially, I'm going to have either an acute angle or an obtuse angle, which would result in an acute triangle or an obtuse triangle. So in our last result, we had a squared plus b squared, which ended up being 1 unit more than c squared. It still was more. They weren't equal, so it wasn't a right triangle. But in that case, that resulted in what we would call an acute triangle. All three angles are under 90 degrees. It probably would have been very, very close in that case because 1521 was awfully close to 1520, but it would still be acute nonetheless. If my a squared plus b squared ended up less than the c squared side, that would be a case where it would be an obtuse triangle. In other words, one of the angles is greater than 90 degrees. And again, it kind of goes without saying at this point, but if the a squared plus b squared equaled the c squared, that would be the case where it is specifically a right triangle, just like in the first couple of examples. All right, so this last problem actually uses a previous concept that I'll just briefly cover. In this case, in this example, we are given 3 segment lengths. Kind of like if I gave you 3 boards to use for construction or something like that. Maybe you're framing a roof or something. But I give you 3 segment lengths. One that's 4.3 feet, one that's 5.2 feet, and one that's 6.1 feet. The very first part of this problem says to first verify that these 3 segment lengths can in fact form a triangle. What does that mean? It means that it is possible to take 3 segments that cannot form a triangle. Let me demonstrate. Okay, let me say that like you had some long board that you set on the ground like that. And then you have kind of 2 shorter boards. One that did this, and you like maybe you're making a pillow fort or something like that, and like this is the floor down here, and this represents one of the pillows. And then you had another short one like right here. Now what you'll be able to see is that if I were to try and take these two, the red and the green segment right here, and I were to try and like lean them against each other, notice that they're going to fall way short and just collapse down onto this blue side. It's important to understand here, this is part of the abstract aspect, the geometric aspect with this unit. But it's important to understand here that it's not possible for me to just take any 3 segments and make a triangle perfectly, rather. Okay, I can do it in ways that overlap and stuff. But if I were to take these 3 and like hook them up at their corners and try and make a triangle out of this, these 2 guys here would simply collapse onto the blue one, and I would just be left with a line. That's what it's talking about here. Okay, so when it says to verify that these can actually form a triangle, how do I do that? I have a little note about it here. This is something that was probably glossed over in a previous geometry unit, but it's worth mentioning right here, just at a fundamental level. In order for a triangle to exist with 3 segment lengths, 3 locked in segment lengths, no overlap or anything like that, the sum of any 2 sides, in other words, if I were to add up the lengths of any 2 sides, it would have to exceed or be greater than the length of the 3rd side. So what does that mean here? Given these 3 lengths, if I were to add any 2 of them together, it would have to be more than the 3rd length. So in this case, 4.3 plus 5.2 would have to be bigger than 6.1. 5.2 plus 6.1 would have to be bigger than 4.3. And 4.3 plus 6.1 would have to be bigger than 5.2. So I could show work for each of those sums and confirm that, yes, in fact, all 3 situations each of the two other sides will add up to make a longer amount than the third side. All that does is it verifies that I can, in fact, make a triangle with those three side lengths. Okay, so what? I can make a triangle with those three. Now what? Is this triangle a right triangle, an acute triangle, or an obtuse triangle? So I have made a triangle officially by hooking up the corners of each of these. And I'm going to get some resulting value, like some resulting looking triangle based on these side lengths. Can I determine whether or not it's right, acute, or obtuse? Yes, I can, using the Pythagorean theorem. The only trick would have to be is which of these three sides would have to be the hypotenuse if it is a right triangle. And as I've said before a couple times now, it's worth repeating that of the three segments, the longest of the three, the 6.1 here, would have to be the hypotenuse, because the hypotenuse has to be the longest side because it's opposite the largest angle. Because in a right triangle, that largest angle would be 90 degrees. So in this case, I could designate A and B being either one of these. It does not matter. C would have to be the 6.1 feet. So if I did A squared plus B squared and then C squared, and the reason I didn't have equals there is because in this case, I'm essentially trying to figure out which side is bigger or smaller or equal. And so in this case, I could have the 4.3 as my A, I could have the 5.2 as my B, and then the C would have to be the 6.1. This is essentially the only one that's important to lock in. And then I have to figure out whether or not these two are equal, bigger than, less than, and essentially at this point, it's just calculator work. So let me do that really fast. 4.3 squared, or 4.3 times 4.3 gives me the following. 4.3 squared gives me 18.49. 5.2 squared gives me 27.04. And finally, 6.1 squared gives me 37.21. And again, I'm just kind of comparing, like, are these equal, greater than, less than? Let's find out. Well, I can combine these two. So 18.49 plus 27.04 gives me 45.53. And the C squared was still 37.21. My job here is now to compare these two numbers. They obviously don't equal each other. So right off the bat, this is not a right triangle. A squared plus B squared did not equal C squared. But now furthermore, this A squared plus B squared ended up being bigger than the C squared. What does that mean? Looking back at our notes, just scrolling up a little bit here, if A squared plus B squared was bigger than C squared, that means I'm dealing with an acute triangle. So yes, these three lengths do make a triangle. That triangle would have to be an acute triangle because A squared plus B squared was bigger than C squared. All right, but that's how we can use Pythagorean theorem in multiple different ways. That will conclude our section 1 notes, so I'll go ahead and stop recording right there.